So to finish, we'll just look at a topic that of course you've been familiar with since your GCSE years, Le Chatelier's principle. Take a system that's at equilibrium, perturb it, and it responds in such a way as to unperturb itself, as to use up that perturbation. So, nice general question here. For the reaction 2SO2 plus O2 goes to reversibly 2SO3 gas. All of them are gases. Delta H is less than 0. In other words, going from left to right is exothermic. Which change will increase the fraction of SO3 in the reaction mixture? Well, we want to drive the reaction to the right because we want to increase the amount of SO3. Now, if we increase the pressure, increasing the pressure means that a reaction wants to decrease the pressure. The only way a reaction can decrease the pressure is to have fewer gas molecules. So increasing the pressure, the reaction goes, any reaction goes to the side with fewer gas molecules. Here you've got 3 gas molecules on the left, 2 on the right, so it will go to the right. So that looks pretty good. Now, increasing the temperature, well, any reaction, when you increase the temperature, would like to use up that heat. The way it uses up the extra heat is to go in the endothermic direction. Endothermic direction here is to the left because I told you delta H is less than 0, which applies to the reaction written according to as the reaction is written. So therefore to the right is exo, so to the left is endo, so that's yucky. Adding the catalyst does absolutely nothing to an equilibrium position. It just means you get to equilibrium more quickly. So the only one that's going to increase the SO3 by driving the reaction to the right is 1. Now this nice question here, which is kind of a silly question in a way, provided a way for me to just summarize everything. So we've got exothermic reaction. So in other words, going in this direction, it's exothermic. 2CO gas plus O2 gas goes to 2CO2 gas. So we're talking about doing a stress. What stresses can we do? Well, we can add a reactant. If we add a reactant, we've got too much on the left-hand side, so that means the reaction tries to use up that reactant by going to the right. Okay, so in such a case, the amount of reactants would decrease, the amount of products would increase. If we add a product, now we've got too much stuff on the right, so it wants to go to the left. Okay, so the reaction will go to the left. As it goes to the left, it will increase the reactants and decrease the products. So therefore, adding reactant or product, right, will change both the concentrations of reactants and products. Keeping going. Remove a reactant. Now we've reduced what's on the left. We want to increase what's on the left. The only way we increase what's on the left is by the reaction going to the left to make up some more of the things that were removed. So again, increase the reactants, decrease the products. Same idea if we remove products. Now we don't have enough on the right. The reaction's got to go to the right to make that up. The way that that happens is it uses up reactants and makes products. If we heat a reaction up, any reaction goes to the endothermic direction. Well, here we're told it's exothermic in that direction, so to the left will be endothermic. Again, increased reactants, decreased products. If we cool it down, the opposite takes place. Cool any reaction down by taking away heat. The reaction tries to make that heat. That means it goes exothermic, which in this case is to the right. Decrease reactants, increase the products. Now, if we increase the volume, that's the same as decreasing the pressure, okay? And if we decrease the pressure, the reaction wants to increase the pressure again, which means it goes to the side with more molecules. So we increase the volume, it's like decreasing the pressure. In this case here, you've got 3 molecules of gas on the left, only 2 on the right. So to make more molecules, so you go to the left. We know what that does. Decreasing the volume is the same as increasing the pressure. The reaction wants to decrease the pressure, which means it makes fewer molecules, which in this case goes to the right. And we know what that does. So in other words, any of those stresses is going to change the concentrations both of reactants and products. Decreasing the temperature at equilibrium. Okay, we've already said that if we decrease the temperature at equilibrium, then the reaction, any reaction, will go to the exothermic direction. So that's the first 3 possibilities, and these blue ones going to the endothermic are not options anymore. Now then the rest of the question, or each answer, talks about the rate. Well, with any reaction, when you decrease the temperature, you slow down the reactions. So we're going to slow down both of the reactions, both the forward and the reverse reaction. It's just we slow down the exothermic one less than we slow down the endothermic one. So the answer here was the first one, A. So the following reaction at equilibrium, if the volume is doubled, so in other words, increase the volume, then that means decrease the pressure. If we decrease the pressure, the reaction goes to the side with more molecules. And in this particular case, there's 4 on the left, 2 on the right. So in this case, it will go to the left. Now then, if we add more N2, or if we add more N2, we're adding a reactant. If we add a reactant to the reaction, we affect the equilibrium position, as long as that reactant is part of the equilibrium considerations. So we add reactant, drives the reaction to the right. So therefore the answer here is double the volume goes to the left, add more N2 goes to the right. Now question 28, my answer key is going to look funky because when I actually use this particular reaction, this particular question in an exam, I had every single possible permutation on it. So again, it's worthwhile looking at every single possible permutation, okay? And here are the various answers one could have done. So anyway, let's see what we got. We got one gas going to 2 gases, and we're told it's endothermic, which means that going to the right is endothermic, so going to the left is exothermic. So any reaction, when you add a reactant, as long as that reactant is part of the equilibrium considerations, reaction's going to go to the right. And if it goes to the right, it makes more products. Add a product, as long as that product is part of the equilibrium considerations, you've got too many products, reaction will go to the left, making more reactants. Remove reactant, well, as long as that reactant is part of the equilibrium considerations, then you need to make more of it, which means the reaction goes to the left, making those more reactants. Same argument with the product, need to make more products, reaction goes to the right. If you add heat, any reaction goes in the endothermic direction. Here we turned endothermic is going to the right, so therefore it will make more products. Cool it down, any reaction goes in the exothermic direction. Here we're told endothermic's that way, so exothermic must be to the left. So therefore we would make more reactants. Increase the volume. Well, increasing the volume decreases the pressure. Any reaction will go to the side with more gases to increase the pressure up again. Here we got 1 gas on the left, 2 on the right, so here we'll go to the right to make more gases, so more products. Obviously flip around, decreasing the volume increases the pressure. Any reaction goes to the side with less gas to try to decrease the pressure again. Here again, 1 gas on the left, 2 gas on the right, so here the reaction will go to the left. Now there's also, if you add a catalyst, it does nothing to the equilibrium, and if you add an inert gas, it does nothing to the equilibrium because it's not actually changing the partial pressures or the concentrations of the reactant and product gases. Now it is worth just pointing out the possible answers, just in case you do some multiple choice questions at some point in your life. Always worthwhile eliminating the silly ones. You can see here we've got going to the right makes more products. Every time we talk about to the right, that's in red, we make more products. So therefore, if the reaction goes to the right, it certainly doesn't make more reactants. So you can eliminate that one before you even start thinking. Similarly, we see in the blues, every time the reaction goes to the left, by definition, it makes more reactants. So you can eliminate this answer, reaction will go to the left, making more products, because that just doesn't happen. And generally, unless you've got the catalyst or inert gas, which are not going to do anything anyway, there will be a change to the equilibrium, except under a few specific conditions. And sometimes we'll even talk about that in these future questions. So in which reaction will the amount of reactants present increase with an increase in the reaction container volume? So if we increase the volume, we decrease the pressure. For any reaction, it wants to increase the pressure, which means it tries to make more gas molecules. So it will go to the side with more gas molecules. And therefore, as we want it to go to the reactant side, we want to the reaction that has the reactant side with more gas molecules. Well, we look at the first one on the left, 2 on the right, none on the left, 1 on the right, 2 on the left, 2 on the right, so that's no use. That would not change when you change the pressure or the volume. Again, 2 and 2. And then we got 4 on the left, 2 on the right. So this will be the one, the only one of these ones listed that when you increase the volume, thus decrease the pressure, you'll send it to the left. This one here, you want to get it, if you increase the volume, so you decrease the pressure, the reaction will go to the right, because there's 2 to 1. Reaction will go to the right, because the only gas is on the right. Nothing would happen, nothing would happen. That goes back to the point on the previous question. And so the only one in which increase in the volume, so decrease in the pressure, will send it to the reactant side, is the last one. So this is a fun one, given that for this particular equilibrium, give you the values of Kp as a function of temperature. So as we increase the temperature, K decreases. Okay, so increase the temperature, K decreases. How does K decrease? It means the reaction must go to the left. So as we increase the temperature, the reaction goes to the left. Okay, and going to the left means it goes towards the reactants. So increase the temperature, reaction goes in the endothermic direction for any reaction. Thus, in this particular reaction, increase the temperature, the reaction goes to the left. Thus, endothermic is to the left, or the reverse reaction. Exothermic is the reverse reaction, or the forward reaction. So the possible answers there, right? As we increase the temperature, we know that K is decreasing. That means it shifts towards reactants. Seen as that any reaction goes to the endothermic direction when you increase the temperature. That means exothermic is to the right, the forward direction. Or we could say the equilibrium shifts towards the products as the temperature decreases, because if we're decreasing the temperature, K would increase, which means it goes to the right, goes towards the products. Either way though, because of how the K changes when T changes, the reaction's exothermic in the forward direction. And finally, a few questions ago I said generally when you make a change to the amounts, to the temperature, to the pressure, you'll get a change. Although there are some times when you won't get a change, and we already talked about with gases, change the volume and pressure, you won't get a change if you've got equal number of gases on both sides. Well, this is an example here in which changing the amounts will not change equilibrium. Told we're doubling the amount of tin. And so the unwary student will say, oh, look, tin is a product. So if I increase the amount of tin, I'll drive the reaction to the left. And if I drive the reaction to the left, and I'll be using up CO2, so the partial pressure of CO2 will go down. I really understand this stuff. Trouble is, though, tin is a solid. As it's a solid, it has no effect on anything to do with the equilibrium. Thus, the partial pressure of CO2 will remain the same. Same argument if you mess with the amount of solid tin 4 oxide. Hopefully, this made some of the questions a little bit easier to understand.